Thank you for the introduction. It's my honor to be here to introduce your recent work on the charge transfer dynamics and spin result potential energy surfaces. So in the late 19th century, when Thomson first discovered the electron, he made a toast at the Cavendish lab that says, "To the electron may it never be of use to anybody," presumably joking about this newly discovered abstract concept of electron appears to have no apparent application at that time. Now, when the time moved to today, while I'm not 100% sure whether electron has been of useful to anyone else, I'm pretty sure that it will be very useful to me because the topics I'm going to talk about today, they will all be related to the electrons. In fact, I'll talk about the charge transfer reactions. I'll talk about the conservation laws that include both the nucleus and the electrons. And I will also talk about the spin result potential energy surfaces. So by integrating these three pieces together, our goal here is to develop a method that one can use to study the spin dynamics in charge transfer problems. One example of this kind is the Cis effect, or what we call it a chiral-induced spin selectivity effect, where people have found that the unpolarized electrons, when they transmit through a chiral molecule, they could become spin polarized. Now, in this pioneered work, the researchers discovered that those unpolarized photoelectrons generated on the gold substrate surfaces, when it transmitted through a monolayer of chiral DNA molecules, they could observe that the spin polarization can be greater than 60%. So this is the kind of the problem that we want to play a role into. Now let's jump to our main topic. The first thing is the charge transfer. We all know that charge transfer is a very important phenomenon that happens almost everywhere in our lives, such as catalysis, electrolysis, photosynthesis, combustion reactions, etc., etc. Now, given that it's an important role in society, studying charge transfer can be very challenging for the reason that on the experimental side, it's a transient state that happens very fast. So one would need a very high time resolution to probe it. Whereas on the theory side, charge transfer naturally requires information about excited state that can be very expensive to compute. So what we want to deliver into this field here today is we want to propose a method that can be that one can use to study charge transfer and run non-adiabatic dynamics very efficiently. So I will talk about the radical system here as a start. Since we focus on the efficiency, our goal is to use a minimum possible number of configurations that one can ever reach to study charge transfer. And obviously, we have to include at least two configurations, one for electron, one for donor, and one for acceptor. And even within that setup, there are two scenarios that one could either have a case of electron transfer, where the two configurations would look like one configuration is the one electron excitation of the other, versus one can have a case of a hole transfer, where we would excite the hole into a lower energy shells. But in either case, whether donor transfer or whether electron transfer or hole transfer, a natural thing to think about is then to minimize the weighted sum of the energies of both configurations, like either these two here or either these two. Now, if one were to do so, for example, say for this phenoxyl-phenol system, where one can move the hydrogen in between these two oxygens, and there will be a charge transfer happen. What we find though is that the potential energy surfaces that we would get for those two configurations will not be smooth. So that's not something we want. Yet a further analysis showed that such a discontinuity on the potential energy surfaces is in fact not some disaster that cannot be avoided, but rather something that can be treated with a proper prescription. What I mean is, if we look at the orbitals we find on this curve, where in the region that is close to the crossing, the two active orbitals, the ones that are being excited ones, they actually correspond to a charge transfer states. As you can see that they are localized on different rings. The real problem is in the range that is far away from the crossing, where if you plot the orbitals, you will find that they correspond to two orbitals on the same ring, which means this is a local excitation. So a natural thought would be, if one can find a way to avoid the local excitation, we might still be able to use this minimum number of configurations to study charge transfer. And after some study, we find that the best way to impose such a constraint is to put constraint on the vector space spanned by the active orbitals, or equivalently, the density matrix of those active orbitals, rather than simply the orbitals themselves. The specific thing we propose is that we impose the vector space spanned by the active orbitals, or say the density matrix of the active orbitals has to project equally onto the two molecular fragments. And I draw a picture here where PL and PR corresponds to the basis space from different molecular fragments, and the P active here is simply the density matrix of the active orbital. So to help with understanding this constraint, I have two limiting cases for the case of charge transfer, where two active orbitals could be localized on different rings, or they could both be delocalized on two rings, but they have in-phase and out-of-phase linear combination of these two cases. Now one can verify that these two cases actually would have the same density matrix in terms of active orbitals, and they will both satisfy this condition. Whereas if there were a local excitation as we've seen before, then both orbitals would be localized on the same ring, which would mean that one of the term here would be 0 and the other term here would be 2. So this constraint will not satisfy. So by having such a constraint, we can remove local excitations, but it also makes it to be a constraint, makes our problem become a constraint optimization problem. But if we do so, we immediately get what we want. Now in this plot, I also draw the potential energies of two states where our results are in black, and we're comparing with a reference that is in red. We show that for such a system with this constraint optimization, we can get the energy gap correctly in the avoided crossing region. We can also get a good position of the geometry, a good position of the minimum geometry. And the analysis on the orbitals also shows that the physics is also correct. Whereas if we move the hydrogen, say here, in between these two oxygens, now from left to right, we see that one charge actually moves from one ring to the other. So that's all suggests that our method works well in the weakly coupled charge transfer problems. And surprisingly, our method also works well in the strongly coupled region. Well, this molecule is an example where experiments have shown that detaching these two fragments corresponds to a strongly coupled charge transfer processes. And if we use our method to study these processes, where still we show the ground state potential energy surface using our method in black. Now it matches pretty well with the one that find using using a larger active space, whereas the constraint DFT appears cannot capture the proper landscape. We believe the reason is that the constraint we put we believe that the reason is that we don't require a predefined diabatic scheme to define the diabates so that we can capture the adiabates also well. And the further analysis on the dipole moment and also the diabatic coupling confirms that the state we found does correspond to a strongly coupled charge transfer state. So up to this point, I hope I have convinced you that we have got a method that it is indeed possible to use two configurations to study the charge transfer problem. And what we're going to do next is then to push the efficiency of the method to its limit. Now we have found a way to make the cost of this constraint optimization problem to be only on the order of the ground state level series. We have also made it possible to compute the analytic nuclear gradients as well as the derivative coupling also on the cost of ground state level theories, which are essential for running non-adiabatic dynamics. And we also extended the method such that we can study the charge transfer across multiple charge centers. For example, charge transfer across a chain. Now with all these pieces, here I'll show you one example as a proof of concept that we can indeed run non-adiabatic dynamics, where I performed the surface hopping dynamics simulation for the proton transfer in this phenoxyl-phenol ring, where we will prepare the system to be first in its a fully relaxed state, and then we will excite it to the first electronic excited state, and then let the system evolve. The dynamics we've seen suggests that the system quickly drops from the excited state to the ground state within approximately 10 femtoseconds. And within the same time frame, if we look at the geometry data, especially the distance between the hydrogen and this oxygen that are shown in this blue curve, we find that the hydrogen also travels from one side of the ring to the other side. So this suggests that the system, in fact, goes through almost 100% diabatic process that directly go from this point to that point here. And if we further look into all the trajectories, we find that after this hydrogen reaches a minimum point near the oxygen here, it then bounces back and trying to transfer back to the ring. But because it has dissipated a lot of energy into the ring here, it couldn't transfer back and has to oscillate back and forth around this oxygen. And note that for the results I'm showing here, each point here only requires computational cost on the order of ground state level theory, which essentially is like 40 seconds for on a one-node cluster. So this is very efficient. So we are happy about these results because it shows that we indeed have a method now to run non-adiabatic dynamics in a very efficient way. But when we try to examine some properties of our result, we find something that's a bit odd. No, what we find is that, say, for these processes, if we compute the momentum of the system, we should have expected that the total momentum is a constant as a function of time. And that's indeed what happened for the nuclear momentum. But when we try to compute the momentum for the electrons, what I mean is we can compute the time derivative of the expectation value of the position operator for electron. We find that instead of being a constant, it's actually oscillating, which suggests that the electronic momentum is not conserved in this trajectory. So this seems to show that something is not right. But what we find that in fact, the problem is not in the non-adiabatic dynamics we run, nor is not in the constraints we put, but rather it's rooted in the bond of Hamiltonian that we choose. To solve this puzzle, please allow me to walk you to our next session where I will re-examine the conservation of total linear and angular momentum. So when we say bond of Hamiltonian or the BO dynamics, what really we mean is that the Hamiltonian for electron is parameterized by the nuclear geometry, and so does the potential energy is solely parameterized by the nuclear geometry. And also the nuclear geometry is evolved under the Newton's equation. And we all know that for an isolated system that is governed by Newton's equation, the momentum should be conserved. For example, if I have lithium and fluorine, we let it collide and become lithium plus and fluorine minus. The Newton's law told us that the momentum before and after the collision should be conserved. But what is hidden inside the BO Hamiltonian is that, in fact, the BO Hamiltonian would set the momentum of electron to 0 in most of the cases. In other cases, for BO Hamiltonian, there's no distinction between moving the atom to the left or to the right. The consequence would be that if we consider the electrons in this system and compute the total momentum of this whole system together, we will find that the total momentum is not conserved on the trajectory that we find from the BO dynamics. And in order to assign the momentum to the electrons and make the total momentum conserved, we actually have to go somewhere that is beyond the BO framework. And that is indeed what people have tried when they propose a phase-space Hamiltonian. So what they will do is they will say, okay, instead of having the BO terms in the Hamiltonian, we should also have the terms that looks like a direct coupling ones, which would couple our ground electronic state to some excited electronic states. And we also need to account for the nuclear gradient of the excited electronic states. while such a phase-phase Hamiltonian indeed assigns momentum to electron and make the total momentum of electron plus nuclear conserved. You can see there is a lot of issues because we need excited states information that can be very expensive to compute. We also need to compute the gradient of excited states that numerically very unstable, which together would make it not suitable for dynamic simulations. So what we find is that there is in fact a way to define a one electron operator to replace this many-body operator such that it will still conserve the total electron plus nuclear linear and angular momentum, as long as this one electron operator satisfies certain conditions, where I will still call it a gamma term. Now, these two equations, while it looks a bit hard to understand, but it means something very, very simple. That if we think of this one electron operator as some kind of a field on this, then this equation says that that field has to be attached to the molecule, meaning that it will move with the molecule and it will rotate along with the molecule. Besides these two conditions, this one electron operator also has to satisfy another two conditions, that it interacts with the electron linear and angular momentum in the way that satisfies the conservation laws. So although these equations looks complicated to satisfy, we have indeed found a way to build a one electron operator that satisfies this. And once we use such a one electron operator and put that into the phase-phase Hamiltonian, we can show that if we run dynamics on these phase-space surfaces, what I mean is, say, actually now our space is not only parameterized by nuclear geometry, but also momentum. And we have to run dynamics following not the Newton's equation, but rather Hamilton's equation of motion, that we have both gradient for the nuclear momentum and the position, which seems to add a bit one more layer of complexity to the BO dynamics. But if we do run so, then we will find that the total linear momentum is conserved, and so does the total angular momentum is conserved. So we can go back and check our calculations using this Hamiltonian, and we can confirm that the linear momentum it does conserve, because it just means we can compute the translation of electrons and the nuclear together. But when we try to examine the angular momentum, a natural question arises is whether the spin should be included in the angular momentum or not. And it turns out it's indeed a very good question to ask and also deserves a careful thinking through. So we know that if we don't consider SOC, then the spin orientation does not talk to the spatial part at all. And in fact, to some extent, we can treat the spin degrees of freedom almost separately from the rest part of degrees of freedom. But if we do consider SOC, as literally being said, spin would couple to the electronic angular momentum. But from the total conservation laws of the electron plus nuclear angular momentum and also the phase-phase Hamiltonian, we know that the electronic momentum will also couple to the nuclear momentum. So we will end up with having a conclusion that spin actually must couple to the nuclear momentum as well. Now, this statement here brings many things interesting. One example is if we think about the Cramer's degeneracy, which says that any open shell systems should be at least doubly degenerate, because the one state and its time reversal pairs should always have the same energy. For example, oxygen triplet pointing up would be identical, would be energetically degenerate to oxygen triplet state pointing down. But the statement here that the spin would couple to the nuclear momentum and also that the electronic momentum would couple to the nuclear momentum actually means that if the molecule is moving, it will break the Cramer's degeneracy. And that's exactly the kind of physics that we are very interested in and we want to look into, which means that we have to do a version update on the previous framework that we have developed. Now, the new requirements here would be that because the SOC, the molecular orbitals are no longer in a pure state, and because the molecules are moving, each orbital would split into two non-degenerate states. And to track, and which also means that we need to track both the orbitals and their time reversal pairs. And also to keep track of the Cramer's degenerate pairs, we also have to keep track of not only the two charge transfer states, but also their time reversal electronic configuration states. I will draw a picture here to summarize what we have here, where instead of the previous picture, we now have then each electron will now have that the electrons will no longer be in a spin pure state, and each of the orbitals will split into two non-degenerate orbitals. And instead of considering only the two charge transfer states, we also need to consider their time reversal pairs. Now, this framework seems sounds quite complicated, but there's indeed an elegant way to include all of this information and keep all the necessary symmetries as well. And if we want to do so, we now reach a point where we can integrate all three parts together, and we come up with a formal Lagrangian that we can use to solve the questions we're interested in. Where this constraint here we seen before ensures that we're starting the charge transfer problem. The Hamiltonian here, we will put in the phase space Hamiltonian such that it will encode the electronic linear angular momentum into the wave function. And the four states here we'll consider that we'll keep track of the spin characters of each surfaces as well as the surfaces that are previously degenerate. So everything is set up, and I will show you some effect of the nuclear motions. Now, in this example, I still use phenoxyphenol, and then we can assign a global rotation to this molecule. And I want to remind you that the molecule is not in a plane, but it behaves something like this. And we're rotating around the z-axis here. And we can rotate either counterclockwise or clockwise. Now, if we plot the potential energy surfaces for the previous two states that we look at a couple of times, when we change the angular velocity, as we do here, we will find that the previously double degenerate surface now indeed becomes four surfaces. So we see now not just the two surfaces, but actually four surfaces will be crossing for a system with a finite rotational velocity. Well, the embarrassing point though is about the energy scale, because to see 1 MeV energy gap on this surface, we actually need to inject 1 EV of rotation energy into the system, which is not quite practical.
A couple minutes left.
Okay. Though I do find some from the non-adiabatic dynamics data we had before, I do find that there is indeed some cases that makes it possible. That is, we can compute the velocity of the hydrogen from this curve by computing its slope, for example. And then we can make a plot that adding a dimension to the potential energy surface plot, where besides the hydrogen displacement, I can also assign velocities to hydrogen because we're doing a phase space calculation. Now, if I plot this, if I plot the curve by projecting these surfaces to a plane defined by, say, the hydrogen velocity, what we end up with is some plot like this, where you can see that within the range of hydrogen velocity that one can practically visit in this in this photon transfer processes, there is indeed a region that we can see, say, like a 1 MeV splitting of the previously degenerate surfaces. Now, when we argue that the 1 MeV splitting is not enough to see things interesting in nuclear dynamics, the important information is that such a 1 MeV splitting of those previously degenerate surfaces make it possible, make things different such that now those surfaces will have a well-defined spin characters. And most importantly, those spin characters would depend actively on the motions that we have, so that one can run spin dynamics for charge transfer problems. And if we go back and finally, I hope I have give you a sense, even just generally, that we now have a method to study the spin dynamics in charge transfer problems. And as a side note, I also find that with this method, we can also deal with something else. For example, the lambda doubling experiments are interesting. And also I have defined that our next speaker, Professor Ni, has recently published a paper about the hyperfine to rotational energy transfer, which is highly relevant to our method. And there's a higher chance we can play a role also there. So if people want to know more and discuss more with me, please don't hesitate to send an email. And finally, I would like to thank Joe's group and all the funding agencies. Thank you.
All right. Thank you so much for the excellent talk. We have some time for questions. We have two options for questions. First is using the Q&A feature down at the bottom of the Zoom window. You can type a question there, or you can raise your hand and we can actually have you unmute and ask your question using the Zoom raise hand feature. But I guess to kick off the discussion, I guess one question I have is going from the methods that you're introducing, how much more expensive does that make the non-adiabatic dynamics?
So as I mentioned, we have so each point here on this say like non-adiabatic curve would require say want to compute the electronic structure as well as the gradient, which is the analytic gradient of the potential energy surfaces. And we have optimized the method such that they both be on the same order of cost as the ground state level series. So if we do Hartree-Fock, then it's the same as the Hartree-Fock ground state calculations, or on the same order. It's a factor of like 3 or 4 to that. And if you give some practical data, like for this system here, 1 point on a one node will take around 40 seconds to 50 seconds to compute.
Okay. Thank you. We have a question in the Q&A from Lishan Liu. Has the phase space method been linked to dynamic simulation?
Sorry?
In the Q&A, we have a question from Lishan Liu, which is, has the phase space method been linked to dynamic simulation, is the question.
How is it or has it? Well, so the phase space is involved in the dynamics in the way that, so if you look at it here, basically in BOs, then the equation, the surface will be parameterized only by the nucleus. So we do Newton's equation of motion. But in a phase space, we will have, they say the potential energy surfaces being a function of both nuclear and the moment, both nuclear geometry and the position, nuclear position and momentum. So one can use Hamilton's equation of motion, where we take a gradient of the potential energy surface with respect to momentum to take as a change of the nuclear position, and we will take a minus gradient of the position of the potential energy surface as a change of the momentum, which, yes. Right.
Cool. Thank you. And then we have another question from Lingqing Peng. Could you discuss more how this method could potentially be used to study the nuclear spin nuclear rotation coupling in Professor Nee's work?
I don't have a solid defined plan to study that, but I believe it's possible. I don't have slides for that, but I believe it's possible that if we have the conservation laws for electrons and the nucleus, but if we can expand it such that to include also the nuclear spins into the grand picture, such that everything will couple together. That's probably one approach one can use to extend and study the hyperfine rotational energy transfers, just in a similar way as what we did for spins.
Perfect. Thank you so much. I guess there's one quick final question from Kwang Hyun Cho. Are there any classical analogs of the phase space Hamiltonian? And this will be the last question.
Okay. The classical analog of phase space Hamiltonian. You can think of it as this force field as some kind of like what is called inner, for example, like a centrifugal force or that kind of thing. Like you're moving, you're viewing yourself in a in a system where you have acceleration, so you will have a fictitious accelerated forces. That this force field is in some sense mimicking that kind of thing, so that the electrons will know that the system is moving and accelerating and rotating. They will respond to that. Maybe I'm not sure if that would be a good answer to your question, but that's the first impression I would have to give you how would it look like think about it in a classical way.
Perfect. Thank you so much again for your talk. And now Nathan is going to introduce our next speaker.
So as Professor Kankwan Ni is getting her slides shared here, in the meantime, let me go ahead and introduce her. So Kankwan Ni is the T.W. Richards Professor of Chemistry and Professor of Physics at Harvard University. She received her PhD from the University of Colorado at Boulder. And her group develops techniques to bring selected molecules to a standstill and to develop new interrogation schemes to study quantum nature. And this includes entanglements and reactions, using molecules as quantum building blocks of complex systems to harness reactions for quantum resources. And with that, I will give the floor over to Kankwan.
Great, thank you so much for the introduction and for the invitation to speak at this seminar series. And also thank to Tian for the last talk to also highlight some of the things that is relevant for his work related to ours. Unfortunately, I won't be able to speaking of that work, although it's it's somewhat related, just because there's not enough time. So in my group, we have developed a lot of control over atoms and molecules, very simple molecules made out of really made out of two atoms, and for example, on the top panels here, we show individual pictures of individual atoms that we can arrange and then in interesting geometries, and engineer their interactions to study ideas in the context of quantum simulation and quantum information. And one of the work that I will not be speaking but just very quickly mention is that we're able to assemble individual atoms into individual molecule, as shown on this sort of traps with laser light going through the microscope objective, and have them interact via dipole interactions, and also allow them to entangle and perform a quantum logic gate. So a lot of this technology is very much related to a lot of the work that we do, but today I will focus on the work that's highlighted in this picture on the left, where we would like to explore the role of nuclear spins, quantum coherence, and entanglement in in these molecules, which we can prepare at extremely low temperature. So it's sort of the idea, and I'll elaborate more, is that if we have a chemical reaction, such as depicted here, two caribou molecules come together, going through reaction complex to go to reaction products, then can an entanglement between the atoms, let's say that the red one and the blue one that are entangled, both up, plus down, down, after a chemical reaction, after these reactants are now distributed into product, but two separate molecules, whether they can stay entangled. So that's an overarching questions that we would like to get a handle on. We're not going to be able to answer that question because that's it's a very difficult question to answer, and one needs very rigorous measurements and things like that. But we are making progress toward really answering some pieces of that overarching question. Okay, so let me just start with one slide of introductions. This year we celebrate 100 years of quantum molecular physics and chemistry. And the field really started, 100 years ago, where, for example, this is a excerpt from Professor Dudley Hirschbach's Nobel Prize lecture, where, he noted that, the field really started with, say, Alter Stern, which with the development of molecular beam techniques to be able to really allow us to beginning to probe isolated atoms and molecules, isolating atoms and molecules in vacuum chamber, such we can really begin to probe their intrinsic property. And then a slew of innovative techniques and demonstrations since then. Stern-Gerlach experiment, Rabi oscillations, Ramsey separated oscillatory field methods, so on and so forth, and including Professor Dudley Hirschbach's own cross-molecular beam experiment, allowing us to really examine and study collision with collision chemical reaction at single collision events. So we're building on these set of tools and continue to have more and more control and manipulation of atoms and molecules. What I will focus on today is to ask the question of whether we can, general question of whether we can harness chemical reaction for quantum science. In specific question that I want to ask, as I already alluded at the very beginning, is that reactions turns into product going through reaction complex, whether these products are entangled. Of course, that's a grand question, so we want to break it down into simpler question that we can begin to make some progress. For example, can coherence be maintained throughout such a reactions? That's the question that we actually want to answer and can answer in some specific context. And if so, we can leverage it to generate entangled products. So the idea is to entangle spins within molecules and then use chemical reaction to break up the initial molecule into separate entangled products. So here I give an outline of my talk, which is really a list of what we need to really show that such to examine such a question. So we need to begin with molecule in a single quantum state, so we can for example prepare them in an entangled state. And then we need a chemical reaction to break up such a molecule into products. We need to detect the states of the products so that we can tease out any we can know, we can tease out any quantum correlation, but it's actually not just the quantum state of the product, but rather we actually need coincident detection of the product so that the products are coming from the single chemical reaction events to allow us to tease out on to tease out like unusual quantum correlation as opposed to being washed out by ensemble average. And then of course, it seems like if reaction dynamic is chaotic, that's very difficult to actually, it's unlikely leading to an entangled product. So we want to avoid such a scenario and check to see ultimately whether, have a way of checking to see whether coherence can survive such a reaction. So this is the outline of my talk, and I'll go through each bullet point here one by one. So molecule in a single quantum state, the approach that we take actually follow the work that when I was a PhD student and Gila, we demonstrated that with potassium rubidium molecule assembled from microscopically individually atoms, even though it was a bulk gas, we can prepare through various coherent control approach, which I'm not going to get into detail, but the important thing is that we're able to have a trapped gas and molecule in a single and the lowest hyperfine rotation vibration electronic ground state, so all quantum degrees of freedom. The lowest hyperfine state is not crucial as long as in a single hyperfine state, which we can manipulate with microwave. And we can take an image, for example, such as the following one shown here. We can do a direct absorption imaging of the molecule, or turn the molecule back to atom to image to get information about the temperature as well as the number information. What was really surprising actually at the time is once we create such a molecule in the lowest energy states, lowest energy for that molecule, they're actually going away in pairs. And this actually was a puzzle because we at the time only able to see molecule in that particular state that we prepare, and we couldn't really know what's going on other than to make theoretical suggestions. So when I started my group at Harvard, we've decided that we want to actually look into detail of what happened to that gas that are slowly going away on the order of second time scale. So I was joined by excellent PhD students and postdocs listed over here, who are now moving on to their own career to build such an apparatus where we, on the one hand, had the AMO techniques to prepare these reactants in a very specific quantum state, and on the other hand, had the more general physical chemistry tool sets to probe the reactions. Okay, so this is what the actual apparatus and all the laser and optics associated with such an experiment actually look like in the lab. So even though I'm telling you a very simple ideas, that we're trying to probe, and you can see that conceptually simple ideas actually need to be realized with much more complex apparatus, because all the real life complexity has to be managed and under control. Okay, so now just a little bit about this detection. So what we usually have is a molecular gas that we prepare using these techniques that was already pioneered in Gila, and we can zap it with UV light to photoionize it, and running these and with these electrodes push into the MCP, we can do time of flight to get the mass information. But in addition to that, we also borrow the technique that's prevalent in the physical chemistry community to arrange these electrodes in velocity map imaging sort of the way that allow us to also, in addition to mass spec, to also get the kinetic information of this whatever we're ionizing here. So turns out these are all very useful, complementary information that we often draw to really tease out all the information we need. Okay, so that's a little bit about our systems. And once we put together such an apparatus, indeed we found that there is chemical reactions in the gas of KRB at ultra cold temperature of sort of 500 nanokelvins, and leading to reaction product. And this was one of the reasons that the gas of KRB was going away initially that was observed. But it turns out it was not the only reason, because it turns out there's also the production of the complex where something can happen already at the stage of complex. So I won't get into too much detail. If we can allow the reaction to proceed in the dark, then we see these reaction product K2 and RB2. Now, with such a reactions, we can beginning to think about detecting the quantum state of the product. And it turns out for these reactions, the exothermicity is quite low. It's only about 10 wave number, or equivalently 10 Kelvin. So it's insufficient to excite vibration, and only excitation in rotations are allowed, which makes it possible to map out, all the quantum states, all the rotation excitation of such a chemical reaction. So we go for the Rampey scheme, the state selected 2-photon ionization scheme, where in the first photon allow us to identify the rotation states of the reaction products, and the second photon allow us to ionize the product and register on our detector. Okay, so this is how we do what we do to detect the quantum states. In addition, like I say, it's very important to tease out quantum correlation and utilizing, to really see quantum correlation, we need to be able to get information from the same reaction product pair. So we use we use coincident detection. So simultaneously we can look for reaction product in specific quantum pair channels, and they will land on our detector because these reactions are coming from a single chemical reaction event. They had to respect momentum conservation, which is the criteria that we use to sort of filter our counts in both X, Y, and Z direction. So if we were to look for a particular product pair channel, maybe we collect data like this many, but after we apply the momentum conservation constraint, and these are the ones that fulfill those criteria, so you can kind of see that every pair, basically you can draw a line, that goes right to the center with the right momentum ratio. So with this, we are able to sort of the tool set is complete to be able to tease out reaction product quantum states and pairs is specifically from the same reaction event. So this was so once we have these tools, what we did right away is actually map out all the quantum states. So there turns out the initial state that we prepared, there's 57 possible outcomes that are labeled by the quantum state of the rubidium dimer and the quantum state of the potassium dimers. And this we could compare to statistical models, because there is a long-lived complex here, and we expect, the sort of the best, the easiest thing to do is to assume that every possible quantum state outcomes are equally likely to be populated, and because there's some degeneracy associated with that, so it's not every state is one, but there's the microstates associated with that. So for the comparison, without getting too much details, we can do a very detailed comparison between our measurement and a statistical model, and found that 50 out of 57 pairs are matching with expectation. But because we have such detailed comparison, we also see deviation. But that's a different story. The main point here is that the distribution is mostly statistical, indicating a chaotic dynamic for the rotation in the reaction. Okay, so this brings me back to this page of outline. I go through all of these points so far, but now we need to avoid chaotic dynamic, and the rotation degrees of freedom sort of shows these statistical behavior. So it's very unlikely that we'll find entangled or coherent natures in that degrees of freedom. So we decided to look into the nuclear spin degrees of freedom. And for nuclear spins, for these chemical reactions, actually, we cannot directly detect them, but their information can be actually mapped onto the parity of the rotation state, which is something that we can detect directly. So, for example, in a chemical reaction between these, let's say these two molecules, if the spins are completely conserved its orientation, let's say, the red is pointing down, afterwards we get with a symmetric spin combination, while blue atoms, pointing the other way, but then after they pair out, this again is a symmetric spin combination. If the nuclear spin orientation does not change, we end up with symmetric spin combination, and because these dimers are indistinguishable nuclei, depends on their quantum statistic being bosonic or fermionic. That symmetric spins will demand that the rotation part of the wave function to be either even or odd, depends on bosonic nuclei or fermionic statistics. Okay, so basically by detecting the quantum states, even the parity of the rotation state, even or odd, we infer the symmetry of the spin being symmetric or antisymmetric. Okay, so this is our work to show that we can change that composition of the initial nuclear spin state, without getting into too much details. And we were able to show that these composition, alpha, beta, gamma, can actually map onto the subsequent, expectation of the rotation parity of the product. So the most important thing is nuclear spin are a spectator in these reactions, so likely not participating in the chemical reaction. But this was mapped sort of in the idea of looking at population, so it doesn't really tell us anything about the phase information. So that's something we want to look into when we sort of get into the question of whether the reaction coherence is maintained. Okay, so this gets me to the sort of the main result, which is, again, I show you this picture before, if we prepare entangled spins with each molecule, so red entangled with blue, in our case, we just ran the magnetic field from, some initial preparation field down to something on the order of, 5 gauss or so. Then we use chemical reaction to rearrange the atom into separate molecule, and whether that coherence or entanglement will be preserved. And the specific question we ask is really just the phase coherence part. Okay, so assume such a coherent process survive. We can do an analysis to see what we expect. So we're using a very sort of represented spin 1/2, as an example, potassium, rubidium, that identically prepare, A and B molecules identically prepare. If chemical reaction is nothing but exchange their partner without even touching the spin, then we can, write out this products, this tensor product into this 4-term. And we also know that because potassium, A and B, or rubidium A and B actually are indistinguishable. So we can't, write it in this, we need to write it in a combined spin basis. So we need to properly symmetrize that. And when we do that, the outcome, which is kind of characterized down here, will show up as actually there will be destructive interference. Because when we combine the spin, there will be a combination with the plus and the minus Clebsch-Gordon coefficient that give rise to this destructive interference. Okay, but if the coherence is not maintained, if the process is incoherent, then everything is just add as amplitude as opposed to everything is just add as population, and there's no phase information, and therefore we would not expect to see any destructive interference for a particular set of channels. And these channels are the even, and odd channels. Okay. So now we have a way to distinguish whether the reaction, outcome would maintain coherence or not by looking at whether, we see destructive interference or not in specific parity channels. Okay, so in our case, we work with 5 gauss, start with a pure state, which has a combination of alpha, beta, gamma superposition. It's not exactly this 1/2 situation, but, nevertheless, we can do the same math. We pick a rotation state pair to represent our even and odd parity. Those are the ones that has the most outcome. And then we calculate for expectations, whether expectation of what we will see in the fully coherent case, 0.7, 0.3 for the even odd and odd even case, and even and odd will be 0. And for fully incoherent case, we had these possibility. And you can note that if we didn't have a way to distinguish reaction from the same event, if I just say potassium is in the even, I don't care about rubidium, and that will be summing these up, and you can see that we're not able to distinguish the process being coherent or incoherent. So it's very important to be able to do the coincident detection to tease out that non-trivial quantum correlation. Okay, at this point, I wanted to pause for a quick few seconds. Maybe, to think for you, what would be your guess before I reveal our answer? Okay, just give you 5 seconds while I drink some water to write down your own guess of what the expectation would be. Okay, so now we do an experiment and to check what nature gives us. And we look at for all these channels, and you can see that there is actually indeed large number of counts in these even odd and odd even channels. And actually it's very small number of counts in the even odd, certainly much less. And as experimentalists, we're being careful. This is kind of screaming out that these are basically background. And the question is, where does background come from? It turns out there's 2-photon ionization process, so mimicking these channels. So when we take that into account with analysis, we were able to, subtract that background, and basically let's represent all the data in this one plot in comparison with coherent and statistical mixture of predictions. And you can see that we were able to show that coherence is maintained. It's basically in the range of 1 with 95% confidence level. Okay, so now this is exciting because we now look in the nucleus spin degrees of freedom in this particular case that we check, and we did see coherent surviving reactions, and this imply, not rigorous shown that the products are entangled, but not, again, will require much more rigorous tests to show that they're entangled. So let me just, the last brief words is there are some, of course, some open question. First entanglement need to be shown with direct phase measurement. So we wanted to be able to do that and not just only measure population. Right now, we map the phase information into constructed destructive reaction channel. So that's how we get some information, but not all the information. And the question would be, what would break the phase coherence of a reaction? Now we see the phase coherence is maintained. What will actually break it? And it's giving us a new way of scrutinizing the short-range physics when everything comes together. What can actually cause this nucleus spin to dephase? And if our phenomena is even general, and what about reaction in much warmer or even in liquid condition where nucleus spin is still very isolated from other degrees of freedom? But the conditions are much more natural for usual reactions. And then think about what we can actually harness reactions for quantum application. So let me just to say that it turns out our finding was, if we change the initial superposition state and no longer in an energy eigenstate, we actually don't see a clear coherent or incoherent or coherent or statistical mixture prediction outcome. So it certainly is not general. So there's certainly something that could break the phase, and we're trying to figure out why. And in particular, let me just say one of the things that we're actively working on now is to start with a cloud, split them into two, and for one of them, put a phase, relative phase between the two clouds, and allow them to combine, these reaction interferometer idea and find out what the outcome would look like as a function of this phase that we alter. So I'm not going to get into the detail. We're just beginning to take data of this. So this way we, not the same as actually measuring the phase of the outcome, but we deliberately changing the phase initially for the collision, and we're looking for, what the outcome would be to learn more about, what actually matters in these reactions. Okay, with that, let me just thank you for your attention, and give thanks to all the people in my group who's actually doing this work. Thank you.
Wonderful talk. Thank you, Kangwen. So we have time here for a couple of questions. Just a reminder that if you'd like to ask a question, you're welcome to use the Q&A feature button down below to type in your question, or you can also raise your hand and we will unmute you to ask your question. Well, maybe to kind of get things started here, I think you may have answered my question already. So I wondered if you had changed the initial state, how you're preparing these reactants. Does it show similar statistical to non-statistical outcomes that you were showing kind of it's mapping onto these 57 different outcome possibilities, and you showed 50 and 7. Does that change as you change the initial states?
Yeah, so
Preparation?
that experiment is hard to do. It's data intensive. Basically, we took data for 2 or 3 months continuously to really have this full mapping. So we have not done the experiment where we change the initial states, although that would be interesting. So I think it is very difficult to know why certain channels are deviating, and I'm not totally sure whether experimentally varying something is the way to do it. because
Yeah.
there's actually no theory, beyond the statistical model. Now we need something more precise, and there's no theory that we can compare to. So it is a very data intensive. So for the most part, it is statistical, but we are able to tease out a few channels that are none, and we don't really know why. Yeah.
Yeah. Very good. So I have a question here in the chat from Yu Liu. Does the chaoticity of a reaction's dynamics necessarily lead to decoherence in the rotation of vibrational degrees of freedom? I would still think that since each reaction is a unitary process, i.e. no dissipation, the coherence in any degrees of freedom is preserved.
Yeah, that's a very good question. Yu was, I don't know, this must be the Yu that was the one who actually built the apparatus initially. Right. So I think if I talk to, when I talk to theorists, they always say like everything is unitary. So like, everything is coherence and entangle for sure is there. But the question is, whether one can show it. I would say we don't know whether rotation or vibration degrees of freedom is really chaotic, like not leading to any coherence preserving. It's certainly much harder to show because there's, for example, 57 channels, so you have to show their phase, relative phase is very difficult. And the fact that, our nucleus spin, coherence preserving the nucleus spin, and we use the rotation parity to map on to give us information. It is also suggesting that the coherence has to be somewhat preserved, or at least the parity of the coherence has to be preserved in the rotation degrees of freedom. So I think it's difficult to show, but it's certainly it doesn't mean it's not there. It's just very difficult to show. Yeah.
Perfect. All right. I think we have time for one more question. If there's any other questions. Tian, I'm going to unmute you. Please go ahead.
A very nice talk, Professor Li. I have a question about if is it possible to apply a magnetic field among these processes and say by changing the direction or say the amplitude of magnetic field? Could that be serve as some kind of weak or strong measurement that would influence whether it's coherent or not?
Right. So in our case, we do have 5 gals, and I think in some of these other measurements that we were it's not really shown here. In one of some of these measurements that we've shown with different spin composition, we were worried about whether spin projection preserving, it's the thing that matters to leading to statistical mixture outcomes. So we also were able to go to like 50 gals or something like that, much more higher magnetic field to try these experiments. But I won't say that there is actually a consistent picture to see what actually alters things. So it seems like this general notion of not an energy eigenstate might be the one that can summarize this, but there is not really any, anything finer to say like, okay, the total projection is changed or things like that. Yeah.
Thank you.
Good. And
We just
just
need more experimental information. Yeah.
And just one last question here from the audience. Will electron spin have any effects in the reaction's dynamics?
Yeah, that's a very good question. So in our case, these molecules are all closed shells. So they are not directly involved, but when they're in the complex, then in principle, electron spin can play a role. But what that time scale would be, it's not clear. So that's why we're probing experiment. It's kind of pointing to it's not, but in some scenario, in some scenario, coherence is not maintaining. So why that is, we don't really have a clue. So that's why we're doing the experiment where we deliberately changing the phase and see what happens. But if anyone has any ideas, we'd be very happy to hear.
Perfect. Well, thank you so much, Kang Ni, for giving an excellent talk, and thank you again, Tian, Chu, for an excellent talk as well. So just a reminder that as we wrap up here, that the next seminar will be November 14th. Look forward to seeing everybody at the next one. Thank you, everybody, for attending.